Typically install these instruments in the morning in a laboratory, and they're running samples in the afternoon. So in fact, it takes less expertise to run this mass spectrometer than it does a triple quad mass spec. Let me show you a couple of examples just of very interesting studies, I think. First of all, let me take 6 pesticides that all have the same nominal mass. Now, the same nominal mass means they all have a molecular weight of 288 point something. These are all 6 pesticides over here, and there is their calculated true molecular weight. Now, if you have a quadrupole mass spectrometer or an MSMS mass spec, or if you have a time of flight, you cannot tell the difference between those different pesticides. And you notice that here you've got the molecular weight out to 4 decimal places. So like this one is 1474. That means that last 4 is accurate to 0.1 millimass units. 0.1 millimass. Okay. So let's assume that we've got all 6 pesticides. Now, how did I calculate these exact masses up here? Well, I simply take the 9 carbons, and there's the true accurate atomic weight of carbon, and the same thing for hydrogen, and the same thing for nitrogen and oxygen. Now notice with atomic weights you actually have 6 decimal places of accuracy to work with. Okay? And that's well known and well characterized. So with atomic weights you've got 6 decimal places. So now what we're saying is that experimental mass spectrometry is coming within 1 part per million of the same accurate result. So let me show you what happens. Now, if I take this mixture of 6 pesticides, John, I see what you mean. Okay, and I run this in a typical mass spectrometer, like a time of flight mass spectrometer. I'll run at about 10,000 resolution. And what you see here is follow the black line. I've got one peak here, and I've got a shoulder here, and I've got another peak here. But in fact, I really don't know what I've got because there's a whole lot of co-eluting, if you will, pesticides because they all have the same nominal mass. That's why they're all going to appear about the same mass range. Okay? So that won't give me a lot of information. If I go to 20,000 resolution, and that's what the state of the art in time of flight mass spectrometry is right now. The QTOF mass spectrometers will go to about 30,000 resolution. But at this nominal resolution of 20 or 30,000, I think you can see that in fact I now get 1, 2, 3 peaks. But again, I can't distinguish all those pesticides because the spectroscopic resolution is not high enough. Now, if I go to 100,000 resolution, which is available only through this exactive mass spectrometer, then in fact I can identify all 8 pesticides, even though they all have the same nominal molecular weight. They have the same nominal molecular weight, but different exact molecular weights. For example, if you're up closer and you look in your notebooks, this last peak out here, the mass spectrometer says I have a molecular weight of 289.1547. 0.1547. Now, if I go back and I calculate the exact molecular weight, actually the exact molecular weight of that peak is 289.1552. That means that I have an error in measuring that molecular weight of 0.05 millimass units. That's 0.1 part per million. That's absolutely unbelievable. That's 0.1 part per million mass accuracy. And when you look this up in the Merck index, you'll find only 1 compound in the world with that molecular weight. Now, when I come back to Korea in the spring, I fully expect to come back with a software package that allows you now to search the whole Merck index for all organic compounds. Because now we're looking at total unknowns, and that's why you need the Merck index, also because the Merck index reports their molecular weights out to the same degree of accuracy. So we think that that will be a major new search tool. Well, just a couple of other examples, and I'll conclude. One of them is here. If you have again pesticides with the same nominal mass, and now you have a mixture of these that's not 1 to 1 to 1. Let's say that we have one part of the methoxin over here, and I have 3 parts of parathion over here. So this is a 3 to 1 mixture. Now notice that the molecular weight is 292.0. Here the molecular weight is 292.0. So in fact, they have almost exactly the same molecular weight. Now if you put them in this mixture, what you'll find is that, of course, there's 3 parts of this and 1 part of that. So this big hump here is mostly parathion. And in the way it comes out, if you measure the mass right there on the back side of the peak, you'll get an error of about 5 parts per million. Okay, and all I can say is you were pretty lucky. If you measure it on the front side of the peak where this red line is, now you've got a true mixture of the 2 pesticides, and now the mass measurement error in the parathion is 42 parts per million. That's absolutely useless. Okay, so what you need to do is increase the resolution up to 100,000 to 1, and as the resolution goes up, now you get 2 beautiful peaks, regardless of the concentration, because they're very well separated, and you see that the mass measurement error in that peak is 1 part per million, and in the parathion peak, it's 1 part per million. Okay, so this is taking a very, very complex situation of 2 identical pesticides in molecular weight, and now mixing them in a 3 to 1 mixture, and being able to determine the molecular weights to a part per million. I think what I'd like to do is just show you very quickly something that really surprised me, and that was taking a look at some of the matrix effects that came out of a laboratory in the Netherlands. And that's shown right here. Now this is a veterinary drug residue, and it's in a matrix of horse feed. And horse feed means grains and vitamins and straw and so forth. And horse feed becomes horse feed byproducts later. So you've got quite a complex matrix, is my point. And what I wanted you to see is that when you look for this veterinary drug, I tended to look right at that peak right there because I thought it was the major component. Well, it's not the major component, and I would have identified the wrong peak if I had not had the accurate mass of this peak right here. And the accurate mass there says I'm within 1.4 parts per million of correctly identifying a very large veterinary drug residue. Now, if I have lower resolution, here's the same spectra run at 10,000 resolution, and now I don't learn anything because I can't measure anything. So it really says that high mass accuracy, I think, is important today to solving a lot of analytical problems. And many of these are in your book, so I won't stop to go through these. What I'd like to do is just simply conclude with the results of the study that came out of the Netherlands. And this is the Reichelt Laboratory, which is one of the national reference laboratories in the European Union. And this is a laboratory that has got a lot of excellent mass spectrometry experience and expertise in food safety. And what they did was they did a study where they took 151 pesticides, mycotoxins, and veterinary drugs. They just mixed them all up in this straw, in this horse feed. Okay? And then they set out to see how many of the 151 compounds could you identify using exact mass spectrometry, accurate mass. Well, the green bar over here says that they were able to identify 100% of all of those 151 compounds in the horse feed. And in fact, if you're down to about 10,000 resolution, you're able to identify about 86% of the mixture. Now notice that the concentration here is in parts per billion. Parts per billion. As the concentration goes down to 10 or 20 parts per billion, then you see with the accurate mass at 100,000 resolution, you've identified 99% of all those mixtures in the same matrix accurately, whereas with the lower resolution, you get about half of the compounds identified correctly. So it really does depend on the resolution that you've got. And so I think that that is an exciting time because this is a major change in being able to identify non-targeted compounds, because non-targeted compounds are truly, truly unknown, and the only way to really identify them with confirmation is when you know the accurate molecular weight. Okay, so I'll just have to close with my favorite slide that shows you, again, the beer sample taken from the Czech Republic, where they did a side-by-side comparison of a time-of-flight mass spectrometer, again looking for mycotoxins in beer. The only sample I've seen them run is beer. Okay, they know more about beer and mass spectrometry than I'll never know. So here's the time of flight, and what you see is as the concentration goes down, pretty soon you lose the peak altogether here because you don't have the specificity of about 10,000 resolution. At a 100,000 resolution, now in fact you get a good quantitative peak all the way down even to 5 micrograms per liter. So you're getting down to the subpart per billion level of mycotoxins. So with that, I wanted to share something that I think is a major breakthrough. I'm very enthusiastic about it. As we say in our laboratories, when you look at a sample with high mass accuracy, mass spectrometry, you won't miss a single thing because you'll find things you never saw before. With that, I'll close and say thank you very, very much. You've been a great, great audience today, and it's a pleasure to be here, and I look forward to doing it again. Thank you very much.